All right, the wonderful world of time series ETL. Let me start the stopwatch so I don't run over. Okay, Barry, thank you for the introduction. From a show of hands, who here has Postgres in their stacks? Good representation. Let's go in the NoSQL camp. Who here has MongoDB in your stacks? Not as many, but it's still got a decent representation. Who here has something completely exotic that is totally not mainstream? Okay, not that many. Oh, we got a couple. All right, well, for all three of the above, this talk is for you. So just starting things off, who am I and why am I qualified to talk about incremental time series ETL? My name is Bennett Meares. I'm a data engineer. I got my start with utilities data, but I've worked with all kinds of data. I currently am the data engineer at Stratified. We do a lot of text analytics, sentiment analysis, machine learning, all that good stuff. Today's talk is based on my master's thesis research on practical synchronization strategies. Spoiler alert, it depends. I'm also the author of the ETL framework Meerschaum, which is the, living, breathing implementation of these strategies. As data engineers, we like to think of ourselves as these contemplative architects building these shining, leading off into the sunset data pipelines. But the reality of the situation is we're more often than not data plumbers, or we build these weird glued together contraptions. We have to do crazy gymnastics just to get the data flowing again. And this is a screenshot from the film Apollo 13, where the NASA engineers have to put a square peg into a round hole. This talk is broken into two parts, so I'll have to go through really quick if you guys want to get our hands dirty to the in-practice stuff. But the first half we'll take a look at what synchronization is, some of your choices, and then we'll look at some experimental data and pick the winners. So first, what even is time series incremental ETL? Well, ETL is extract, transform, load. Fetch, filter, upsert is just a novel spin on the concept. At the most fundamental level, the three stages are data retrieval. So I represent everything as SQL, but this could be as simple as an API call, where you get all data newer than some timestamp. The filter step is filtering out the duplicates and determining the delta, so which rows have either changed or are net new. And then finally, the upsert stage is either straight up inserting the new rows or applying the updated rows based on the indices. And all of these, yes, if you're not familiar with SQL, don't worry, this applies to most databases generally speaking. Now let's walk through some scenarios. In the ideal case, say we have one ID, so a sensor, a temperature sensor for example, and it reports its reading like clockwork on the hour every hour. It only appends, it doesn't backlog, and it always inserts a new value into its table. In this most ideal case, we can do what I call a simple sync, which is just moving the cursor, determining the start time, and always inserting new rows. So if the green is the source of truth, and the blue is our target that we control, as time goes on and we don't sync, this missing gap will grow. Filling this gap is a trivial case of just finding the most recent time and selecting everything newer than that. In reality, we need a little bit of wiggle room, and so we take the previous start time, we call it now the reference time, we just rewind it a couple minutes or hours or even a day, and then we select newer than that just to catch any stragglers. More often than not, you have more than a single ID. You have these multiplexed data streams, if you will. And if the IDs more or less march in tandem, so here I have two IDs, they're within a few minutes or hours of each other, then that same backtracking strategy will catch the differences in most scenarios. But let's talk about the elephant in the room. How do you handle backlogged data when the past changes on you? So in this case, if we know the bounds, so just this past week, one of our clients said, we've had to throw out everything from July, reprocess everything. It's just a matter of determining a start and an end bound, filter out everything between those intervals, filter out the duplicates, and plug the hole. So we can deal with backlog data if we know the intervals. The same holds true with multiple IDs. So you might have a discontinuous sample of gaps, and you have some more options. You could either do that simple sync on the per ID basis, instead of having to draw a bound here and here, which could span millions or billions of rows. There are pros and cons to doing these discontinuous samples. The TLDR is it depends on how mutable and frequent your data are, but here are some of the three choices you have. You could either just union these subqueries together, you could either do the same logic in the where clause, or you could get fancy with it and do a left join. In the wild, you'll often know that your target is out of sync, but not know where those intervals are. So in that case, we have to iterate across the entire datetime axis. One practical way we can do this is a simple iterative backtrack. We determine the oldest known target time, the newest known target time, so two references, and we split up our axis into chunks, and we can either sync the chunks in parallel or just do them in series like I'm showing on this graph, and that effectively will plug all of the holes. This is kind of what rsync does at a file level. Okay, so we know what synchronization is. Let's actually look at real strategies, starting with the simple syncs. They're all variations on the same basic idea we talked about, simple and simple backtrack, but these three are those ID level ones we talked about. So you could either append the queries together with a union, or you could do a left join, or you could pick the reference time from the slowest reporting ID. On the opposite camp, we have the no compromises accuracy. So if you're working with financial data and you must have certainty, here are the iterative syncs. So we talked about iterative simple. Daily row count sync is partition your entire data axis between the bounds into even chunks. So it doesn't have to be daily, but effectively you would group each chunk into days and resync the days that are out of sync. You could determine those bounds through a binary search. In some scenarios, that's more efficient because if you have wide tables and a very small delta, that could be faster. And finally, it's worth noting, the most interesting but least practical case is CPI sync, which has been proven to be the most bandwidth efficient of the strategies while being horribly inefficient for processing time. So a niche where CPI sync will come into play is if bandwidth is at an absolute premium. Say you have to sync with your satellite and you're paying a penny per kilobyte. You could do the computation, a little bit of linear algebra on the satellite, a little bit here on Earth, and just send the deltas back and forth. And you'll see more of that in the graphs. There's also some caveats because it has to do with prime numbers and it's very situationally dependent. So let's take those two ideas. We've got the fast but potentially inaccurate simple syncs. We've got these slow but very thorough iterative syncs. And if we combine the two, we have these corrective syncs, which boils down to doing a fast simple sync on a regular cadence, so every day or every minute, et cetera. And then on a wider cadence, so once a month, for example, we'll do those more expensive iterative syncs. It's worth noting there are bounded and unbounded variations of the iterative syncs. For example, if your table were to span 25 years, the likelihood of data being backlogged 20 years in the past is quite low. So generally, you could bound it into the last year, and that'll sort of set a ceiling on your runtime. All right, so those are all of our options. Let's look at how they actually perform in a tournament against each other. I put together a simulation and measured the performance in three different metrics: how long it took, how much data went back and forth, and how accurate was the target table. I also tested these four scenarios: the ideal case, a variation of the ideal case with a large number of IDs, the known backlog, so this is just 24 hours things went out, and then the scary unknown random throwing everything at it, unknown backlog. So this could go somewhere far into the past. So let's start with the simple syncs. Because they're so similar, we expect the performance to be more or less neck and neck, but the key outlier here is this purple one. That is simple backtrack sync, which is just a simple rewind. In this case, the sensors, quote unquote, were reporting on a once per 24-hour basis, and the backtrack interval was 24 hours. So that's why we have double the bandwidth required, but we have much higher accuracy as a result. Here are those same metrics boiled down. You can see the bandwidth is much higher, but we get that gain in accuracy. Here's the same tests on the append-only large N. And the point of this is to demonstrate the append and join that I talked about actually perform very quite poorly when you have a large number of IDs, so I don't recommend them for practical use. But backtrack seems to be doing quite well. And here are those same metrics on one single graph. And more or less, you have the same general shape with a little bit of a gap here and there. All right, let's look at the iterative syncs. A lot more spread here. The lime green one is that interesting case CPI sync. So you can see it's neck and neck, just a little bit more bandwidth than simple sync, which is our control. Perfectly accurate, but holy cow, was that slow. That's like 2 orders of magnitude, maybe even 3, than the fast case. So you can see here's our simple sync. This might take a couple seconds to run. This might take a couple hours or days to run. This is the bounded versus the unbounded versions. It all has to do with the probability of backlogging. And effectively, the bounded and unbounded are neck and neck, with the exception of the unbounded performs worse as your data set grows. And here we have a lot more to work with, but even despite its inaccuracy, simple sync actually performs quite well on the normalized readings. All right, let's combine the ideas into the simple syncs. And here at the bottom are the daily simple syncs. So the really fast one, the blue, the control. And then these spikes are the once per month backtracking where we do the entire interval. The gray case here is the naive case. So when you resync the entire table, so just drop the table and start fresh again. And of course, it gets gradually worse and worse every time. But the main thing to point out is this is the accuracy graph, and it has this bouncing effect where it is amortized to 100%, but it's not quite 100% at any given moment. Here's the bounded version. It's quite similar, but there's that ceiling on the runtime and everything. And here are those graphs. Here's where things get interesting. CPI sync obviously being the outlier here, the naive sync being terrible in bandwidth. The bounded variations somewhat moderate those outliers. And here are the relative performances put onto the same graph. So you can see quite clearly which ones are terrible and which ones are good. Okay, we've been through the numbers. I know that was a lot, but I know you just want to know which one should you pick. Now, the summary bar charts, things are all over the place. It's really hard to judge apples and oranges. So we normalize everything into a single index, which is kind of what the circle and triangle graph was doing to compare these different strategies on the same axis. So when we want to optimize for one of the 3 metrics, so we only care about runtime, simple sync is the fastest because it's doing the least work, but it's also the most inaccurate, so I wouldn't pick it. The join sync is actually slightly better than simple sync because it's more ID focused. And then lastly, the iterative syncs are clearly going to be best on accuracy. Let's have a matrix for, let's allow ourselves to have 2 priorities. So first we'll pick, say I care about accuracy first and runtime second. Here's the spread first. So simple, monthly, bounded, simple. I know, not a very simple name, am I right? I thought that was going to get more laughs. But yes, you can see, depending on what our priorities are, the rankings can change quite dramatically. Same thing with 3 different priorities when we spread the weights evenly between all 3. Just the difference of this, you can see the lime green, that's CPI sync. As soon as we consider the 3rd one, it's always last place. That's just how slow it is. So let's pick the cream of the crop. And it really depends on your scenario. I know that's a letdown, but first, when you're asking yourself which strategy is best for me, you have to consider how many IDs you have, how often you're backtracking, how important is accuracy to you, is bandwidth super expensive, like the space situation, and will you be synchronizing often? Because oftentimes a simple backtrack will catch any outliers if backlogging happens on a recent basis. Here's a little screenshot from my thesis where you can pick one. But I've already picked 3 for you. So simple sync, that's the fastest. If you just need some data thrown up on a chart, just do a simple sync. Daily row count sync actually performed better than expected, beating out binary sync in most simulations. And then there's that simple monthly iterative simple bounded. And there they perform together. Here are their performances on the time series charts. Okay, so everyone take a deep breather. We made it to the first half, and we're right at the 15-minute mark. Okay, so this is all great in theory, but we're not here to talk about theory. This isn't an academic conference. We're developers. We write code and we get our hands dirty. So this is where we can put our hands on the keyboard, put something together. If anyone knows Fireship, and do you guys remember he made a video where he sold his AI voice? Well, I bought his AI voice, and I made this parody Meerschaum in 100 seconds. So let's go ahead and watch this. Thank you very much. So yes, that was very fast. You might have some questions, but simply put, it's an ETL framework where you can just focus on the data ingestion. It's all about interfaces, right? We've heard this from other talks. It'll generalize, it'll filter out the duplicates for you, and it'll issue those upserts on your behalf. So in this case, we're fetching from plugin NOAA, just some weather data from weather.gov, and it'll determine which rows have changed or been backfilled and update the table for you. So in this case, plugin NOAA foo is our example pipe, and here I've created plugin NOAA foo just to show you how syncing from weather stations can work. The video mentioned in-place syncs. In a lot of cases, you can represent your transformations entirely in SQL. Think how dbt works, that sort of thing. Or Snowflake, I think, has something like that. So in this case, a SQL main weather Charlotte is chained onto that plugin NOAA foo, but the transformation is all in SQL. So nothing is loaded into RAM, rocketing your performance. Here is the definition of that transformation. So I just want to take the average monthly temperature and convert it into Fahrenheit. Here's that date bounding. It'll take that definition, wrap it into a meta CTE, and perform the date bounding we talked about from the diagrams for you. Now, if you're a Python developer or you're a data scientist and you work with pandas, this is the API for you. Here, you can see we've created SQL main weather Charlotte, which we showed in the previous slide. And getting the data frame is as simple as pipe.getData. So here are those rows we just looked at. Of course, your table might have millions or billions of rows. And so it has support for basic date bounding and querying. Because we designated month as our datetime axis, we can do a simple begin and end query. So greater than March, less than May, that's 3 and 4. You can do a where clause, so give me all Charlotte stations or all stations that are not Charlotte. And this value can be a list, and you can mix and match. The underscore negates the where clause. Here's how upserts work. So if this is our base table, and I want to update this 200, I can just run a sync with a new document with a value of 123.45, and you can see it updates the correct value, 200, to this value, based on the designated indices. So this columns parameter has designated timestamp as the datetime index, and all other keys don't quite matter. They're just a regular immutable index that together, they are all treated as a composite primary key. So if you have a primary key, you're doing great. That makes your life easier. But a lot of times, databases you have to work with don't have a primary key, and this is how you can work with that situation. But here's how upserts work. And a lot of times, especially when you're working with data that touches humans at all, your schema will just completely change on you. You get a new column, things change. Here I'm adding a new column foo, and you can see it just inserts it into the correct place based on the indices. So we can deal with a dynamic schema, which is awesome. All right, here's the fun part of the conversation. In this example project, or often in reality, we have to work with a heterogeneous database fleet, which is a fancy way to say things get messy, data gets built by different teams on one database or another. You have to maintain legacy systems. And your boss has tasked you with tying everything together into some new BI tool that they just bought, thinking it'll solve all their problems. So in this one, we're going to ingest some weather data. We're going to simulate one team building it into Postgres. We'll simulate another team dumping it into MongoDB. And then we'll do the task of marrying these together and doing some ETL. I've put together the Carolina Code Conference repo. You can scan the QR code if you want to follow along or just watch the fireworks. Here it is. So in this example project, I don't have time to go through the entire README, but I do encourage you to clone this and follow along if you can. This example project will have 5 different pipes. First, we're going to pull from plugin NOAA like we saw, and South Carolina stations, and we're going to dump that into Postgres. Really, it's timescale DB, but that's just Postgres. We'll do the same thing for North Carolina, but instead we'll put that on MongoDB because why not? The third one, let's consolidate those 2 data sources into one final, still raw data, but one table on Postgres where we can do more analytics. Then we'll chain on a step of ETL, convert that raw weather data to Fahrenheit, so from Celsius to Fahrenheit, and get rid of some columns we don't care, like barometric pressure and whatnot. And then finally, we will compute a daily average to have some nice, pretty clean, easy to work with values. All right. Who here works with Docker on a regular basis? All right, that's awesome. Docker is not required, but if you are not using Docker, it makes your life a million times easier. So if you work with teams, Docker is so configurable that the established standard is the Docker Compose file. That's just a way to state your services in your expected environment. It's a way you can version control and work across teams. The same concept works with Meerschaum Compose, which the video mentioned. Here's the Meerschaum website, meerschaum.io. And there's a tab specifically for the Compose spec, which is just a regular Meerschaum plugin like any other. And so just like Docker Compose.yaml, we have Meerschaum Compose.yaml. And here you can see those pipes that we had, our boss had listed in the specification. Here's South Carolina, North Carolina, combining them with the open source plugin clone, which makes combining existing pipes easier. You could do this manually with SQL queries, but this is effectively a select all, so you can have multiple input pipes. Then we're actually getting our hands dirty with writing SQL. Here I'm converting this messy temperature column into Fahrenheit. And then finally, we're building off that previous table, which I should mention, the target key is the name of this actual table on the database. So weather underscore Fahrenheit. We want to create a new table, weather underscore average. And this is where timescale DB comes in. You get the time bucket function. And we want to take the average Fahrenheit. So the end result, I had dbeaver open, but I had to restart my laptop right before the talk, because that's how these things can happen. OK, I'm going to switch now. Select all from weather average. OK, this is the end result for the table, where we expect to have a nice clean day column, so everything is zeros, a station, just a human readable location, and then our average temperature. And oops, let's jump over into our terminal. Tell you what, there we go, much easier. OK, so here's the project which I've cloned. Oh. Isn't Wayland awesome, guys? OK. And here's this Meerschaum Compose.yaml. If you don't know what to do and you've just started a new Compose project, run mrsm compose explain, and that will just parse the file and print out the pipes that are defined in the spec. So here's the South Carolina one. You can see here's the stations. It actually expands to this more fully expand metadata, but this is just the data we had to write. And when you run mrsm compose run, that is the initial. All right, and it finished running. So when you run mrsm compose run, that will register the pipes in your YAML file on the databases, on their instances, and it'll sync them one at a time. Now, we're all about speed here, and we want things to run concurrently if they can. So when you run mrsm compose up, just like Docker Compose up, that will actually sync all of the pipes in your YAML concurrently. So often in practice, you will have, like for example, you'll see some errors because things will happen at the same time. Often if one depends on the other, it's commonplace in practice to have multiple Compose files for different projects or different stages of your ETL pipeline. But the end result is that you can have all of them syncing concurrently at the same time, each in their own thread. Now, I want to shift a little bit and take a deeper dive into the code itself. This might be an example finished product of how I remember. Yes, this is what we want to put together in the very end. So this is running on the Meerschaum stack. On my host machine, I just run mrsm stack up-d. That'll start a pre-configured Docker Compose stack for you with timescale DB and Grafana and all that good stuff already set up and interconnected for you. But let's go ahead and refresh, and there we go. We got some new data that just ran while I was fumbling with the pointer. All right, so whether it is great for demonstration purposes, but let's actually look at the code itself, because there's no Python code here. This is just a YAML file with a little bit of SQL. I've actually put together a new starter project. So whenever you clone this, go ahead and dive into carolinacompose.yaml. And I've started a plugin called Fake. So Fake Reviews, this is just to simulate user reviews. And in the plugins file folder here, here's fake.py, which defines a fetch method. One common problem that Meerschaum solves is when you're working with out-of-memory data sets. So you could have gigabytes or terabytes of text that you have to parse through. It all comes down to chunking. So in the video we showed, it just returned a list of documents in all well and good. But in this case, I want to demonstrate that you can also yield documents. And this can allow you can ingest a data set of really any size. And each chunk will be synced in parallel with all the other chunks. So let's take a look at this fetch function. I'm using the Faker library. And it's creating a list of documents, 1 per hour, with the timestamp being hour, some fake text, and then it yields documents. So I'm going to go ahead and run this. I talked a little bit about date bounding. That's what the begin and end flags are for. So here I want to run the Carolina Compose YAML file we were looking at with the fake reviews between the interval of August 1st and September 1st. OK, it'll finish just in time. Here we go. And just as we expected, each line here is a chunk in itself that we yielded. So all of these chunks ran together in parallel. Of course, nothing changed because I've already synced this, but that's why we have an insert of 0 and nothing changed. And with that said, if you enjoyed this talk, I would love your stars on GitHub. It's just Meerschaum on GitHub. And once the talk is over, I'd be happy to talk to you in the lobby. Thank you, everybody, for your time. I appreciate it.